All right, so today we're going to finish up chapter 27. The first thing we're going to do is look at the force on a current carrying wire. So we said yesterday that only moving charges can feel magnetic forces. And since we know that a current is made up of moving charges, that means that a current carrying wire will feel a magnetic force if it's placed in some external magnetic field. So let's figure out what that force actually is. So we know a couple things already. We know that if we have some current carrying wire, we're looking at just a segment of length L here, so just one little segment of that wire. We can figure out what direction the force will be in first of all. So if we say that the current, let's say, is moving upward, if the current's moving up, we can use the right-hand rule from our Lorentz force, because we know that F, magnetic force, is equal to QV cross B. So in this case, for a current carrying wire, we know that the velocity is going to be the drift velocity of those particles, and we're assuming, a little unphysically, that our current carrying particles are positive, since that's the convention. So our current is moving upwards, our positive current carrying particles are moving upwards with some velocity Vd. So this velocity here is the drift velocity. So use the right-hand rule. You put your hand in the direction of the current, which is upward. Move your fingers in the direction of the magnetic field, which in this case, again, we have these little X's, which means it's into the page. So you put your hand in the direction of the magnetic field, which is into the page, and you see that your thumb is pointing to the left. So this segment of wire with some current will feel a force to the left. So, all right, we know the direction of the force. So now let's figure out the magnitude. So we have our velocity and our magnetic field are perpendicular. So we know that the sign is going to be 90 there. So we can just look at the magnitude of this without worrying about any sign, since the sine of 90 is equal to 1. So this is for one particular current carrying particle. But we know that in a segment of wire, there's going to be many particles, right? So there's a bunch of particles in here, all with the same charge and all with the same drift velocity. So to find the total force on this entire segment of wire, we're going to need to multiply, because we have some density of particles n. They all have charge q and are moving at velocity vd. But then we have this volume of wire. So we have this many particles in some volume of wire given by the area here, so the cross-sectional area of our wire A times the length of our wire. So times A times the length is B, and this is the total magnetic force now on this segment of wire, where this was just the force on one particular particle in that wire. So now I can write, or I can notice that NQVD is my current density, and then I have an A here, and the current density times the cross-sectional area is the current. So J times A is the current. So J times A, I can rewrite all of this here, NQVDA, this is all just equal to I, the current. So I times, I still have that length L, times B is going to be my total magnetic force on that wire. So we can write this in more general terms. First, let's look here. So we can write this back as our cross product, since we ignored the sign term when we were doing this, since our wire and our magnetic field were perpendicular. But that doesn't always have to be the case. So in any general case where you have some wire and some magnetic field, you can just write it as the cross product. Now the important thing to note here is that this vector L is in the same direction as the current. So any wire you have, and you have some current going in whatever direction, and the segment of wire is some length L, we give the length the vector part instead of the current. Since current isn't really a vector, this length gets a vector, or gets a direction rather, and so this is our vector here. But it's always in the same direction as the current. So this L is just the length of your wire segment and the direction that your current is moving in. And then we cross that into the magnetic field, the external magnetic field. So we can also write this as an integral or like a differential element. So if we just are looking at some little infinitesimal segment of wire in some different shape, it doesn't have to be perfectly straight. Maybe we're looking at a circular loop or a square or some kind of different shape other than just a perfectly straight line. We can rewrite the force as an integral. So we can write this differential element here. And then if we want to find the total force, we would simply integrate over that wire to find the total force. And we will do a problem where we do integrate so you can see how that works. Okay, so this is the force on a current carrying wire from an external magnetic field. And now this is important. We'll get more into this in chapter 28. Just make sure that you realize that this magnetic field is some external magnetic field. We'll see in chapter 28 that wires produce their own magnetic field. So this B is some different magnetic field. It's not the magnetic field due to the wire itself. Okay, so let's do a simple example using this. So here we have a straight horizontal copper rod carries a current of 50 amps from west to east. Now this is one thing that bothers me about your book is for some reason when they introduce magnetism, they start using like compass directions like north, south, east, west, which like I don't know why they don't just stick to X and Y and Z. So I think that makes it a little bit confusing. So if you get a little bit confused sometimes when they describe the directions, that's okay. Just try to translate it into X, Y, and Z direction. So anyway, so they set up this like map direction. So we have the current basically going from left to right, which would normally be like our X direction. So maybe let's just do that. Okay, so we have our current going from left to right. In this region, there is a horizontal magnetic field towards the northeast. So that would be like in the XY plane here. So our magnetic field is going in this direction. And it's at an angle of 45 degrees with a magnitude of 1.2 Tesla. Find the magnitude and direction of the force on a 1 meter section of rod. So this section of rod over here is 1 meter, and we want to find the total force on it from that magnetic field. So we'll write our F is equal to IL cross B. So the force, the current is just 50 amps. The length they said was 1 meter, so we just plug in 1. And now our magnetic field, so we can rewrite this as ILB, sine of the angle between the current and the magnetic field, since it's a cross product here. So we'll just write B is 1.2 Tesla, and then sine of 45 degrees. So that's going to be square root 2 over 2. So you can plug all this into your calculator, and we get 42.4 newtons is our magnitude. Now you could you can figure out the direction a couple of ways. You can write it as a vector and just do out the cross product the long way, or you could use the right-hand rule. So for the right-hand rule, again, you would just put your hand in the direction of the current, which in this case is like pointing from left to right. So it's pointing sort of away from you like this. And then you curl your fingers towards the direction of the magnetic field, which would be like up a little bit. And then your thumb will be pointing in the direction of the force. So you can see that that's going to be out of the page. If you do it sort of on the page itself, the direction of the force, your thumb will be pointing up away from the page. So this direction is out of the page. All right, now we want to find, while keeping the rod horizontal, how should it be oriented to maximize the magnitude of the force? So you're keeping the rod in this plane, so you don't want to like move it out of the plane. You're keeping it horizontal sort of in this plane here. How should it be oriented to maximize the magnitude of the force? Well, so this is part A. Part B, we can look at it like this and say, okay, well, we know that I, L, and B are not changing, so it just matters the angle that we orient the wire and the magnetic field at. So wherever sine of that angle is maximized, that will be the maximum force. So that's obviously going to happen when that is 90 degrees, right? Because sine of 90 is 1. So it'll happen when they're perpendicular. So when you have the current going that way. Oops, sorry. So if you have the magnetic field going in that direction, kind of at that 45 degrees, it'll be a maximum when the current is perpendicular to it like that. So you might want to orient your wire like that. Okay, so that will be the maximum, and that will be true in any case. Your maximum force will be when the wire and the magnetic field are perfectly perpendicular at 90 degrees. And let's just find the magnitude in this case. So here we'll just have ILB, and then the sine of 90 we said was 1. So the current was just 50, the length was 1, the magnetic field was 1.2 Tesla, and then the sine of 90 was 1. So I'll just put sine of 90 there. And this comes out to 60 newtons. All right, so now we're going to do a slightly more complicated example where we actually have to integrate to find the total force. So we have this sort of like snail-shaped loop of wire here where we have this curved part of radius r, and then we have this flat part of length L, and there's a current I moving through it in this direction. So let's find the force in the straight part first. So we'll call that FL, so in that L length segment. We can see here that the current is going to the left, and the magnetic field is coming out of the page. So when you have these little circles here, that denotes that the field is coming out of the page. So we can use our right-hand rule, put our hand in the direction of the current, so that would be in the leftward direction. And then you curl your fingers up so that they're in the direction of the magnetic field. And then you'll see your thumb is pointing upward this way to the top of the page. So your force, in this case, we have our x, y direction, so your force is in the y direction. And they're perpendicular, so the force will just be ILB sine of 90. So it will just be I, the length of the wire segment, and then the magnitude of the magnetic field, and it will be in the y hat direction. Okay, so now we need to find the force on that curved segment. So we'll call that like FC. So in this case, we have to look at it carefully to figure out what the direction is. So let's look at just this end point here. So if we just look at this end segment here, the current is going like straight up. It's going tangent to this point right here at this bottom point. The current is going straight up. So we can use the right-hand rule. If the current's going straight up at that point, curve our hand in the direction of the magnetic field. Our thumb will be pointing in the direction of the force. So on that one little piece of wire right there, the magnetic force is to the right. And then we can do the same thing at this segment over here. And right over here, we'll see that the force is to the left. Now, these are going to have equal magnitudes because you have the same current and the same magnetic field acting on those little infinitesimal pieces. So the magnitude of the magnetic force will be the same. So you can see that these two vectors perfectly cancel out. So there's no x direction of the force, the magnetic force there. And then you can do that for every single point along your circle. So at this point here, you'll again take your current to be tangent at that point. And if you do the right-hand rule, you'll see that the force is like radially outward in the r direction basically there. And then you'll see that it will break up into, you can break it up into an x and y component. And then if we do the same thing at like sort of the corresponding point over here, so if we want to find the force at that corresponding point, again, take the current to be in the tangent direction here. Put your hand in the direction of the current, curl your fingers in the direction of the magnetic field, and you'll see again that your force will be like sort of in that direction. So you can break it up into the y and x components again, and now you're going to see that for every point along your wire loop, the x component is going to be canceled by the corresponding point on the other side. So sort of just like when we did the electric field of like a disc or a ring, where those x components were canceled by the corresponding one on the other side of the ring, the exact same thing is happening here. So it's the same thing here. You can see that the x component at every single point along this semicircle will be canceled, and only your vertical components will end up adding. So our x component, we can argue by symmetry, is 0. So we'll say f of the curved part in the x direction is 0. Now you could actually set up an integral and do this integral. In your book, they do set up an integral. This is, I think maybe example 27.8. So they do set up an integral to show that the x components really do come out to 0, but we can make a symmetry argument and just say it's 0. So only our y components will be left. So let's do the y components. So we're going to have to integrate. So we're going to have, we had I dl cross b. Okay, and then we're going to have to integrate over our semicircle to find the total force. Now, what we can do, since we want to just find the y component, we see that that will be the opposite side from this angle here. So that will correspond to sine theta. And we can just integrate over this whole semicircle according to theta. So we can integrate with respect to theta. And we want to, so let's rewrite this. So we have I dl b. And we know that everywhere our current and our magnetic field are perpendicular. So the magnitude will just be I dl b. And then we can pluck out the y component by multiplying it by sine theta. So sine theta here. Now I know this is a little bit confusing because we have like two sine thetas or phi's. This is not the sine theta from the cross product. This cross product, our current and our magnetic field are perpendicular everywhere along this semicircle because they're in two different planes. So then we find the magnitude, which is I dl b, and then we're plucking out the y component with this sine theta. So it's very important to understand that those are two different signs we're looking at. This is not the sign from the cross product. So now we have our sine theta, but we're integrating with respect to dl here. So we need to get them in the same variable. And what we can do is dl is like this little part right here. So you can think of that as an arc length, and arc length is written as s times the radius of the circle times this angle theta here. So you might have learned this in like a geometry class or something. So this is how we write arc length. So we can rewrite this dl as r d theta. So we're going to do dl is equal to r d theta. So in this case, when you write arc length with an s, that's analogous to our little dl there. Okay, so I'm going to replace this dl with r d theta. So I get I b r sine theta d theta. And now I can integrate from 0 to pi because I'm integrating over a half circle. So I, b, r are constants, so those come out. Actually, let me write that here. So I, b, r is a constant, and then I'm just left with this. Sine theta d theta from 0 to pi integrates to 2. So this just becomes 2. So I'm left with 2IBR in the y direction as my total force now on this semicircle piece of wire. Okay, so then if you want to find the total force now on this little weird shaped thing that we were looking at, so if you want to find the total force now on this entire thing, you just add up your two pieces. So we had, this was the piece, the contribution from the straight part, and then this was the contribution from the circular part, and we just add them up. So our total magnetic force on this piece of wire is just ILB y hat plus 2IBR y hat, which if we want to rewrite it maybe a little bit more succinctly, we can just write it like this. 2R. So either way you want to write it is okay. So we won't really be doing any integrals that are more complicated than this. Maybe like a quarter circle, and you'll see when we do a full circle, there's actually an easier way to do it. All right, so now let's just do one more sort of conceptual example with the right-hand rule. So here we have sort of this setup. These are like two long wires, and there's like a rail that can slide between them. So this rail here, this can move in either of these two directions. And we can connect a battery to this to create a circuit so that our current can flow through these rails down this rail here and then back into the battery. So that's the setup. And we have a magnetic field, a uniform magnetic field going into the page here. So we want to know which orientation should we set this battery up so that this rail moves to the right. So that means that it will feel a force to the right, a magnetic force to the right. And so which way should we connect the battery, or which way does the current have to flow in order for this rail to feel a rightward force? So let's write down our equation for the force on a wire segment. So let's set up a axis. So we'll call this y and this x, and then out of the page is z. So we want our force to be in the x direction. So let's just write our force has to be in the x direction. And then our current, we don't know what direction it's going to be in. It's either going to be in, obviously, the positive y direction or the negative y direction, right? Because this bar is oriented along the y-axis. So the current can either flow down this way or up this way. So we don't know what direction it has to be in. Now our magnetic field we know is into the page, so that corresponds to the z direction, sorry, the negative z direction, since it's into the page. So we just have to figure out what vector goes here. So if I look at my little x, y, z circle here, so if I have some vector cross negative z gives me x, what vector is that? Well, it has to be y, but is it positive y or negative y? So we can see here that if we just do y cross z, we get x. So if we do negative y cross negative z, we'll get a positive x because those negatives will just cancel out. So this has to be negative y. So if we do negative y cross negative z, those negatives cancel and we get a positive x hat according to our little circle here. So our current has to be flowing in the negative y direction. So our current then must flow downward, which means it's flowing sort of like clockwise like this, which corresponds to putting the positive terminal of your battery up here and the negative terminal down here, because current flows from the positive terminal to the negative terminal. So we want to choose this orientation here. Okay, so we'll see more of this stuff in chapters 29. So let's move on now to the force on a loop of wire. So let's say I have a wire like this, and let's say that there is some magnetic field pointing upward. So I have some uniform magnetic field pointing upward, and let's say that the current in my loop is going this way. So the current is going in this sort of counterclockwise direction. What will be the net force on this loop? So we have to do the right-hand rule. So let's just look at this top segment first. So this top segment, remember we're going to have F is equal to IL cross B. So this top segment, our hand we put in the direction of the current, which is to the left. We curl our fingers upward in the direction of the magnetic field, which in this case is upward. And then our thumb will point into the page. So the force on this segment of wire is like into the page like that. So it's a little hard to draw, obviously, with only 2 dimensions on the paper, but this is into the page. Now let's look at this segment here. So here we have our current is going downward and our magnetic field is going upward. So these are anti-parallel. So if you take the cross product of vectors that are anti-parallel or parallel, if they're in the same plane, the cross product is just going to be 0. So right away we can just say, okay, the force on this segment is 0. So over here, this side is just 0. And now let's look at this bottom segment here. So this bottom segment, our current is going right. So we can use the right hand rule, put our hand in the direction of the current, curl your fingers in the direction of the magnetic field, and we'll see that our force is now sort of in this direction coming out of the page. And now if we look at this segment of wire, again, we can see that the current and the magnetic field are in the same direction, so that cross product has to be 0. So if we look at this from the side, so let's sort of look at this loop of wire from the side. So like pretend we are just looking at it from this direction head on this way. We'll see just that one side of the loop, and it will look like the forces acting on it are like this. So there'll be a force sort of pulling this side this way, and then a force on this bottom one pulling it in the opposite direction, and this looks like a torque. So when we place a wire loop with a current in an external magnetic field, it will feel a torque, just like an electric dipole. All right, so now let's find what the torque actually is. So let's just redraw our little wire loop. So let's say that this side has length B, and let's say this side has length A, and we know that there is a torque, a force in that direction and a force in this direction, so there'll be some torque on this wire. And this is our direction of current. Okay, so we need our equation of torque. So torque, remember, is R cross F, where R is like the distance to where that force is being applied. So in this case, we'll go from the center of our rectangle up to where this force is being applied here. So we can see that this length or this distance is just b over 2, since it's just half of this side. So r is just b over 2. Or let me make that here. So b over 2. And then the force, so let's just write the force here for now. We'll find that in a second, times this force that's being applied. So then this is the force here. And now we have a torque being applied on both the top and bottom of our wire. So we have a torque here, and then we also have a torque being applied down here. But they're the same magnitude, right? Because this distance is also b over 2. So from both sides, we have b over 2. So I'll just multiply that by 2. And now what is the actual force? So remember, this is going to be ILB. Since our current and magnetic field were perpendicular, we can just multiply them. Our magnetic field was up this way. So it's just ILB, and L in this case is just the length of this wire segment, which I said this side is A, so this length here is just A. So I can just replace that with A. And so now let's rewrite this. So our 2's cancel. We have B times I, A times the magnetic field. And then let me just rewrite this a little bit. So we've got I, A times B times the magnetic field. Now, A times B I can rewrite as the area of my loop, right? Because A times B is just the entire area of this wire loop. So I'm going to rewrite this as just the area. So then I can rewrite my total torque on this wire loop as just the current through the loop times the area of the loop times that external magnetic field. Now this actually has a name, so this is something we're going to be using quite a bit. This is the magnetic dipole moment. And we denote that by mu. So a wire loop with a current going through it is a magnetic dipole, and it has a magnetic dipole moment mu, just like we saw with the case of an electric dipole, it had a electric dipole moment. So this is how we denote the magnetic dipole moment with the Greek letter mu. So I just rewrote that here. So our magnetic dipole moment is a vector, and it will be in the same direction as your area vector, which you find by the right-hand rule. So if I have, let's say, some circular loop of wire, and it has some current going through it like this. So if the current is going through it like this, you use your right hand and like wrap your fingers in the direction of the current, and your thumb will be pointing in the direction of mu and also the direction of your area vector. So in this case, our mu will be going up like this. So if your current is sort of going around this way, mu will be in the direction of your thumb. If the current was going in the other way, you would turn your hand in the direction of the current going the other way, and then your thumb would be pointing downward. So that's how we figure out the direction of the magnetic moment, is by just turning your hand in the direction of the current, and your thumb will point in the direction of the magnetic moment. And this is true for any shaped magnetic dipole. We're going to be seeing circular ones a lot. So in the case of a circular wire loop, this area would just be the area of a circle. So let's just say, for example, so just to recap, let's say I have two circular wires, and they have some current going through them. So they have the same radius. But let's say the current in this one is going sort of like around, so that it's coming out of the page here and then going back into the page over here. Whereas this one, the current is going in the opposite direction. So this one, like the current is coming out of the page here and then going back in here. So in this case, mu would be I times pi r squared, and then the direction of that would be upward. So you just, again, curl your hand in the direction of the current. That would be upward in this direction. And then in this one, since our current is going in the opposite way, curl your hand in the opposite direction for the current, and we get, so we'll call that y hat. And this one, you would have the same current times the same area, but your magnetic dipole moment will be downward. And again, it's a little bit hard to draw, obviously, in only 2 dimensions, but that's the best we can do for now. Okay, so now I can rewrite my torque on a wire loop in terms of the cross product of the magnetic dipole moment and that external magnetic field. So while the net force on our wire loop was 0, since all of the forces canceled out, the torque was non-zero. And just like in the case of the electric field and an electric dipole, I can write the potential energy of a magnetic dipole in a magnetic field. And it's the exact same form as the electric dipole case. So the potential energy associated with a magnetic dipole in a uniform external magnetic field is just negative the dipole moment dotted into the magnetic field. So just to recap, if we have some magnetic dipole in the same direction as the magnetic field, the potential energy is given by this, which is UB cosine theta. So in this case, the cosine here is 0 degrees. So we get U is negative mu B, which is the minimum value of our potential energy. So the magnetic dipole will want to align itself in the same direction as the magnetic field. Just like in the case of an electric dipole, the electric dipole wanted to align itself in the direction of the electric field. So same thing. And then here, the torque, we said, is mu B sine theta, and sine of 0 degrees is just 0. So here we have no torque acting on this dipole. Now, if our magnetic dipole is perpendicular to the magnetic field, the potential energy is given by negative mu B cosine of 90. And cosine of 90 is 0. So our potential energy is 0 in this case. And our torque is now at a maximum because sine of 90 is 1. So this is our maximum value of torque here. And now in the case of them being anti-parallel, so if mu is this direction and B is in the opposite direction, our potential energy is negative mu B cosine 180, which is -1. So we have a negative mu B -1, which is positive mu B. So this is our maximum of potential energy here. And again, we have mu B sine of 180 for the torque. Sine of 180 is 0. So we have 0 torque in this configuration, but it's unstable. So this is an unstable configuration for this magnetic dipole. So if there's any little perturbation at all, that dipole will move a little bit, and then it will feel a torque, and then it will align itself in this direction. All right, so now let's do an example with this. So we have a circular coil that's 0.05 meters in radius with 30 turns of wire. And it carries a counterclockwise current of 0.5 amps. So to draw this, what this means is that we have like 30 coils. So these are 30 coils all stacked up here. Each one has a current going through it in the counterclockwise direction like this. And then this is 0.05 meters in radius here. Okay, there is a uniform 1.2 Tesla magnetic field directed towards the right. So it's directed like this. All right, and then we want to find the magnitude of the magnetic moment and the torque on the coil. So the magnetic moment is I times the area. So the magnetic moment is just going to be the current, which is just 5 amps. And then the area, so the area of one of these coils, let's say the top one, is obviously going to be pi r squared, right? But we have 30 turns of that coil, so we actually have to multiply by the number of coils that we have, since we basically have 30 times that original area. So we have 30 times this area, or let me write this as n, where this is the total number of turns or coils. So this is important when you have the magnetic moment of like a bunch of coils or something stacked on top of each other. You have to multiply by the total number of coils because you basically have like 30 individual magnetic dipoles stacked on top of each other. So the total magnetic dipole moment is going to be 30 times that. So whatever number of little individual dipoles you have, you just multiply by the total number of those dipoles, and then you get the total magnetic moment. Okay, so this is going to be, so we just have to multiply out these numbers. So we have 5 amps times pi times 0.05 squared, and then times 30. So that is going to be, that comes out to 1.18 amps meter squared. So this is the magnitude of our magnetic dipole moment, and then the direction is just in this direction relative to the current here. Okay, so that's the magnitude of our moment, and now we just have to find the torque. So the torque, now that we have the magnetic moment, that's easy. So the torque is just mu cross B, but they're in perpendicular planes, so we can just multiply. So we just do mu times B, and mu was 1.18, and B we said was 1.2. So that just comes out to 1.41 newtons meter. Okay, so that is our torque on this entire coil here. So here we have another example. We have a circular coil with now 250 turns. Each one has an area of 2.52 times 10 to the negative 4 meters squared, and it has a current going through it of 100 microamps. The coil is in a uniform magnetic field of 0.85 Tesla, and the dipole moment is aligned with the magnetic field. So I want to know, what is the direction of the current in the wire, and how much work would an external force have to do to rotate the coil so its dipole moment is perpendicular with the magnetic field? Let's just say we have some coil, or coils like this. There's 250 turns here, so N is 250 turns. The dipole moment, they say, is aligned with the magnetic field, so we can just make up, let's just say the magnetic field is upwards since it doesn't tell us what direction. And if our magnetic moment here, so this is mu, if our magnetic moment is in the same direction as the magnetic field, if our thumb is pointing up, that's the direction of our magnetic moment, our hands are curling sort of around this way. So that means that our current would be going this way, where it comes out of the page here, loops around, and then goes into the page over there. So this is the direction of our current. It's like that. Okay, so that's the direction of our current. Now we want to know how much work would an external force have to do to rotate the coil. So we have to use our external force would do the amount of work equal to the change in potential energy. So that would be U final minus U initial. So in this case, our mu final would be, remember U is negative mu dot B. So our final potential energy would be negative mu B cosine 90, because at the end they're perpendicular, minus a negative mu B cosine of 0, because they're initially parallel. So this is 1, this is 0, so we end up with just positive mu times B as our external work. So now what is mu? Well, mu is just going to be the current in each loop of wire times the area of each loop times the total loops that we have. So let's just rewrite that here. So our external work so I times A times N is equal to mu, and then just times that by B. So we can plug in all of our numbers here. The current was 100 times 10 to the negative 6 amps. The area was 2.52 times 10 to the negative 4 meters squared. The number of turns was 250, and the magnetic field was 0.85 Tesla. So this all comes out to 5.35 times 10 to the negative 6 joules. So that's how much work an external force would have to do to move that coil with that magnetic moment and make it perpendicular to the magnetic field. Okay, so now let's look at some applications of some of the stuff we've done already. So for some experiments, particularly if you want to find like the mass of an ion, or as we'll see, the charge to mass ratio of an electron, you need to know what velocity your particles are traveling at. So this setup is called a velocity selector, and basically what it does is you have some particle shoot out here. We've got some charged particle that exits here, and they might have some different velocities. So they don't all have necessarily the same velocity. And what you have is you have two parallel plates so that there's a uniform electric field in this area here. And then you have a magnetic field also, a uniform magnetic field. In this case, the uniform magnetic field is going into the page. And as you shoot these charged particles through, it will basically pluck out only particles with a certain velocity. And now let's see how. So the force on a charged particle due to the electric field, so as this particle moves through this electric field, we know that that force is going to be given by Q times E, right? And if this is a positively charged particles you have here, it's going to feel a force towards this negative plate in the direction of the electric field. Now, it's also going to feel a magnetic force since there's a magnetic field and it's moving. So the magnetic force is going to be given by QV cross B. So if the velocity is downward and it's a positively charged particle, and the magnetic field is into the page, you put your hand in the direction of the velocity, curl your fingers in the direction of the magnetic field, and you'll see that it has a magnetic force. The magnetic force it feels is actually to the right. So the magnetic force that this particle will feel is to the right. So this is to the left, and then this is to the right. So since these are perfectly perpendicular, I can just write it as QVB since the sine of 90 is 1. So you can sort of see here that for some particles, if they have the right velocity, the force it feels from the electric force or the electric field and the force it feels from the magnetic field will be equal. So if we set these equal to each other, so what we want to do is we want to perfectly balance out the leftward electric force and the rightward magnetic force so that these are perfectly equal and this particle can just pass right through these two fields and not even be affected by either one. So it feels zero net force as it goes through here. And what this does basically is, since you can see here that the charge cancels out on both sides, this depends only on the velocity. So if I just solve for the velocity here, I get E over B. So if I have a velocity of some of these charged particles, when they have a velocity that's equal to E over B, they will pass through this undeflected. So the net force that a particle with this velocity will feel is 0, and it will be able to emerge from this sort of cavity here, feeling no force. Now this is useful because it's typically very hard to create subatomic particles that all have a specific velocity. Normally when you create these particles, they have a range of velocities. So this is a good way, if you want to know exactly what the particle's velocity is, you just send it through one of these, and then by knowing the electric and magnetic field, you know exactly what its velocity is, because any other particle, if it doesn't have the right velocity, it might just get sort of pushed over to one of these plates and not make it out, basically. So this is actually how they were able to discover that the electron was a particle. So a guy named J.J. Thomson used this setup to measure the charge to mass ratio, which we'll see in a second, of the electron. And now before this, it wasn't really clear if electrons were like separate subatomic particles. So he was able to show that the electron is actually its own particle. And at this time, once we showed that the electron was an actual particle, the idea we had of an atom was basically that we had just some big positively charged mass, and then we just had all these little electrons sort of floating around inside of it. Now we know that's obviously not the way it is, where we have the positive nucleus at the center and the electrons are on the outside. But at the time, once we discovered electrons, this was sort of how we thought about atoms. It was called the plum pudding model, because they viewed it as the positive charge was like pudding, and then the electrons were like plums in the pudding. So this was how we thought of atoms until we had some more precise experiments and realized that this doesn't work. So one interesting thing is that the man, so J.J. Thomson, who discovered that electrons were actual particles, he won the Nobel Prize for this discovery in, I think, 1906. And his son actually won the Nobel Prize for proving that electrons were waves about 30 years later. So you'll see this in 7E, but the way that J.J. Thomson's son proved that the electron was actually a wave as well as a particle was by shooting a beam of electrons through essentially a very tiny hole and showing that the pattern that emerged was that of a wave pattern. So waves behave in very certain ways where they interact with themselves and diffract. And he showed that electrons do that as well, which is not what you would expect if it was simply a particle. So this is sort of, again, the whole quantum revolution, where we realized that particles were both particles and waves, and it depends sort of on how you look at it, whether it behaves like a particle or a wave. All right, so anyway, so let's look at how J.J. Thomson measured the charge to mass ratio for an electron. So what you do is you accelerate a particle through a potential difference. So this uses conservation of energy. So you have conservation of energy. So you say, okay, in the beginning of this little thing here, my particle is at rest and it's not moving. So your initial kinetic energy is 0, let's say. So all of its energy is potential energy. And it's being accelerated through a potential difference, basically a capacitor. So you can rewrite the potential energy as Q times V. And then at the end of this like capacitor, basically, all of its energy is now kinetic. So all of that energy has been converted to kinetic energy, and it has no potential energy left. So all of its potential energy was converted to kinetic energy, basically from here as it travels over here. So this V, be careful, is the potential V. This V is the velocity V. So what you can do is, since you sent it through a velocity selector, let's write this in terms of this velocity. So let's solve for this velocity here. So we have 2qv, where V is the capital V for potential, over m, is equal to the little velocity squared. So let's take the square root. So we get 2qv over m square root. So that's the particle's velocity when it leaves this velocity selector, which is essentially a capacitor with an additional magnetic field. So this is the particle's velocity. Now, since we sent it through a velocity selector, we know its velocity. We know that its velocity is E over B. So we can write this as E over B. So now in this experiment, since we're trying to find, we didn't know the charge or the mass of the electron, we want to just find, in this experiment, this ratio here. So we want to find the charge to mass ratio. So let's get that by itself. So we have E over B is equal to 2q V of the potential difference over m. And we can square both sides to get rid of that square root. And now we want to just solve and find this ratio by itself. So let's move everything over to the other side. So we have E squared over 2VB squared. And since this is the electron, let's just change that to E for the charge of an electron. Okay, so this is how J.J. Thomson was able to measure the charge to mass ratio of an electron. And since every time he did this experiment, he kept getting the exact same charge to mass ratio, he was able to show that the electron was its own particle with a constant ratio of its charge to mass, since obviously neither of those things are going to change. So this is how we proved that the electron was its own particle. Okay, and now let's just do one example with this. So we want to reproduce this charge to mass ratio experiment that J.J. Thomson did. So we have an accelerating potential of 150 volts and an electric field of 6 times 10 to the 6 newtons per coulomb. How fast do the electrons move? So let's rewrite. So we had our, from conservation of energy, we had this equation. So we want to know, so now that we do know the charge and mass of an electron, we want to know in this setup, how fast were our electrons moving if we accelerated them through a potential difference of 150 volts and the electric field had a magnitude of 6 times 10 to the 6 newtons per coulomb, sorry. So first, let's solve for V here. So we have V squared is equal to 2qv over m. So we can take the square root and get the velocity. So we just have to plug in our charge and mass. So we have 1.6 times 10 to the negative 19 times that 150 volts. And then the mass of an electron is 9.11 times 10 to the negative 31 kilograms. And then we take the square root of all this, and this comes out to 7.27 times 10 to the 6 meters per second. So this is about 2% the speed of light, which is pretty fast. So this is how fast our electrons are moving once we accelerate them through this potential difference. And then we want to know what magnetic field will yield zero beam deflection. So that means what magnetic field do we need to apply so that a particle moving with this velocity, the electric field and magnetic field will perfectly cancel out in that region, and it will just move through undeflected. So we said that that was where we want the electric and magnetic fields to perfectly cancel out. So we said that this comes out to a velocity of E over B. So the velocity, we're looking for B here because we have the velocity and we have the electric field. So we're looking for B, so that will be given by E over V. So the electric field is 6 times 10 to the 6 newtons per coulomb, and our velocity was 7.27 times 10 to the 6. So this comes out to 0.83 Tesla. Okay, so now we're just going to combine our some of our formulas from cyclotron motion and our conservation of energy that we just did. So a mass spectrometer is used to basically measure the mass of unknown or known ions. So unknown mass, known ion. So what we do is we have some source of these ions or whatever particle you're looking at. You accelerate them through some potential difference V. So use that conservation of energy equation here. And then when they enter in this chamber, there's a uniform magnetic field. And then judging by the radius of the arc that they trace out, you can determine their mass. So we have two equations. We have QVB equals mv squared over r from yesterday, which we did during cyclotron motion. And then you have the conservation of energy equation that we just had as well. So QV is equal to 1/2 m little v squared. And so these are our two equations that we're going to use. And here the v's cancel, so we're left with QB is equal to mv over r. So these two equations here are what are used for a mass spectrometer. All right, so let's just do an example to see how this works, one quick example. So we have a magnetic field of 80 millitesla, 1 kilovolt, and the particles are ions with a charge of +1 times the electric charge. So the particle strikes the detector a distance of 1.6254 meters away from its entry point. So let's just rewrite our picture here. What is the mass of the ions? So the first thing to note is that it says that the particle strikes the detector a distance of 1.6 meters away from the entry point. So that means this entire thing is 1.6 meters. So the radius of our circle will be 1/2 that. So let's just find the radius of our circle first. So the radius will just be 1.6254 divided by 2. Okay, so that's our radius. So now let's look at our conservation of energy equation here. So it's accelerated through some potential difference. It has only kinetic energy when it gets here. So let's write its velocity in terms of these things. So we have Q potential difference V is equal to 1/2 m little v velocity squared. And then we also have QB is equal to mv over r from the circular motion part. So let's solve for v velocity here, and then plug this velocity into here, and then we can solve for the mass. So you could do the algebra for this, any way you want. This is just the way that I'm going to do it. So I'm going to solve for this velocity here. So that will give us QBR over M is equal to this velocity. And now I'm just going to plug this in right here. So I'm going to have Q times capital V is equal to 1/2 M, and this is all squared. And then let's simplify this a little bit. So we have QV is equal to 1/2. This m and this m squared down here will cancel. So we're left with q squared, b squared, r squared over m. And we can also see that a q cancels from both sides. So now we want to solve for the mass. So let's solve for the mass. So we have the mass is equal to q b squared r squared over 2 capital V, the voltage. Okay, so we have all of these things. We know the charge was the charge. It has positive 1 electron charge, so that just means it has like the same charge of a proton or something. Okay, so I'm just going to rewrite this on the next page so we have a little bit more room. Okay, so the mass of our particle, Q, was 1.6 times 10 to the negative 19. The magnetic field was 80 millitesla, so that was 10 to the negative 3. The radius, we said, was 1.6254 divided by 2. And that's squared, sorry, and this is also squared. The magnetic field and the radius are both squared. And then 2 times the voltage, which was 1 kilovolt, so that's 10 to the 3. So, okay, you plug all this into your calculator, and this number comes out to 3.386 times 10 to the negative 25 kilogram. So it's significantly heavier than a proton, so it's some ion with obviously multiple protons and neutrons in there. Okay, so this is how you would use a mass spectrometer to find the mass of some ion. Combine the conservation of energy and the cyclotron equation that we had for circular motion in a magnetic field. Okay, so in our next lecture, we're going to start actually calculating magnetic fields. So we'll find the magnetic fields of different current configurations. All right, so I will see you guys next time.